You're listening to an online lecture offered as a supplement to Physics 119A in the fall of 2013. I'm Professor Feigenson. This lecture reviews the derivations presented in Reif, Chapter 3, Sections 6 and 8. These derivations show how entropy changes when systems exchange energy. You'll recall that entropy is the name we give to a parameter S that's proportional to the natural log of the multiplicity. So, in the derivations that follow, our goal is to determine how the natural log of the multiplicity changes when a system's energy changes. This means we'll be thinking a lot about the parameter we call beta, which, as derived in Chapter 3, Section 3, and discussed in lecture, is that special parameter that is equalized among systems in equilibrium. In building our understanding of equilibrium and deriving the parameters S and beta, we found it useful to think about a single isolated system as being composed of two subsystems that can exchange energy. We call these subsystems A and A prime. For the results we'll derive now, we can focus in on only one of the two subsystems. First, let's consider the case in which that subsystem undergoes a purely thermal interaction. To begin, we'll focus on an important special case in which our subsystem of interest, say it's the A prime subsystem, is really, really large. So large that no matter what amount of heat it absorbs or expels, its beta parameter doesn't change. This special case is represented mathematically by the following relation, in which the derivative of beta with respect to energy, multiplied by the amount of energy being exchanged with the system in the form of heat, has a magnitude much, much less than beta itself. When we have a system so large that it's unaffected by exchanging energy with another system, we call it a reservoir. In this case, because the exchange of energy to which our system is robust is in the form of heat, we call it a heat reservoir. The effect of changing the energy of a heat reservoir by an amount Q prime on the entropy of that reservoir can be calculated from a Taylor series expansion of the natural log of its multiplicity. By expanding about E prime, we can find the natural log of the multiplicity at energy E prime plus Q prime. In this equation, I've placed the first term in the expansion, the function evaluated at E prime, on the left-hand side, so that the right-hand side has a first term, which is the derivative of the function evaluated at E prime, times the energy change Q prime. The second term is 1 over 2 factorial times the second derivative of the function evaluated at E prime, times the energy change squared. The third term would be 1 over 3 factorial times the third derivative of the function evaluated at E prime, times the energy change cubed, and so on. Recognizing that this first derivative, the partial derivative of the log of the multiplicity with respect to energy, is just the definition of beta, this right-hand side of the equation can be rewritten in terms of beta. Doing so, we see that the mathematical condition characterizing our heat reservoir implies that the second term is much, much smaller than the first, so that it and all higher-order terms can safely be ignored. Rewriting beta prime as 1 over kt prime and multiplying both sides by k, we get an expression for the change in the entropy of the heat reservoir. It is exactly equal to the amount of heat absorbed divided by the absolute temperature of the reservoir. Notice that this derivation is valid as long as the amount of heat absorbed by the system doesn't change the temperature of the system. This means that A prime doesn't have to be a reservoir. It could be any system if the amount of heat being exchanged is infinitesimally small, which is what happens any step of the way during a quasi-static process. In other words, for any system absorbing an infinitesimal amount of heat, the differential change in entropy will be equal to the differential amount of heat absorbed divided by the absolute temperature of the system during the heat-absorbing process. Now that we know how entropy is affected by a purely thermal interaction, let's consider a purely mechanical interaction. You'll recall that a mechanical interaction takes place when an external parameter is varied. We'll consider varying a single external parameter, x. But because external parameters are independent, these results generalize to situations in which multiple external parameters are varied. Focusing in on just one of the two subsystems again, Let's think about every possible microstate of that subsystem. Every microstate R has an energy, E sub R, that's a function of the external parameter x. This means that when x changes by an infinitesimal amount dx, which is another way of saying when x changes quasi-statically, the energy of state R changes by an amount determined by the derivative of E sub R with respect to x times the differential change in x. So our question really is, what happens to the multiplicity when x changes? Or in other words, what is the partial derivative of the multiplicity function with respect to x? When x changes by some infinitesimal amount, some states that had an energy outside the energy range between E and E plus delta E, and therefore were not counted in the function omega of E, will change enough in energy to enter that energy range. The operational word here is some. The question is, how many? Furthermore, other states that had an energy in the range between E and E plus delta E, and therefore were counted in omega of E, will change in energy so much as to leave that energy range. Again, the question is, how many? To answer these questions and figure out how the multiplicity at energy E changes as x changes, it's helpful to sort all the different microstates of the system according to how quickly their energy changes when x changes. If we plot energy on a vertical axis, then any one particular microstate can be represented as a point, and we can attach to that point a vertical arrow whose magnitude indicates how much that microstate's energy changes upon an infinitesimal change in x. Defining capital Y as the derivative of the microstate's energy with respect to x, the magnitude of the arrow is simply y dx. Now there may be many different microstates, each with a different energy, all of which have a derivative of the same size. The ones we're interested in, the ones that might enter or leave the energy range counted by omega v and x, will have an energy either within y dx of the lower bound of the energy range of omega, or within y dx of the upper bound. We're not interested in any of the other microstates that fall outside these two regions. In order to determine how many such microstates there are, we can start by defining capital omega sub y as the number or multiplicity of microstates whose energy derivative with respect to x lies in the range between y and y plus delta y. Then, the density of states with an energy derivative in this range is lowercase omega sub y, which is equal to capital omega sub y divided by the energy interval dE. And the number of microstates with a y-sized energy derivative that have an energy within y dx of the lower bound, and so are poised to enter the range of interest, is lowercase omega of E times y dx. Finally, the number of microstates with a y-sized energy derivative that have an energy within y dx of the upper bound is lowercase omega of E plus delta E times y dx. If we take the difference of these, represented by lightening the arrows on the states being subtracted, we see that those states whose energy goes from below the energy range of interest to above the energy range of interest cancel out. We're left with a positive count for any states that entered the energy range of the multiplicity, and a negative count for any states that left the energy range of the multiplicity function. The same manner of counting can be applied for any value of y. Here's the same graphical calculation for the subset of states with an orange value of y, somewhat smaller than the blue value we considered before. Some states lie within y dx of the lower bound of the energy range of interest. Some states lie within y dx of the upper bound. And again, you'll notice that any microstate that moves past the energy range of interest ends up canceling out when we take the difference between the two omega y dx terms. The whole calculation is most intuitive when the magnitude of the derivative being considered changes the energy of the associated microstates by an amount that's smaller than delta E. In this case, since the energy change isn't large enough to make a state bypass the energy range altogether, restriction to microstates within y dx of the energy bounds means we only add states that enter the energy range and subtract states that leave. A student once asked, why aren't we considering states whose energy decreases when x increases? But we are. All the calculations we've done are consistent with negative values of y. When y is negative, these formulas count the microstates in an energy range y dx above the lower and upper bounds on the energy range of the multiplicity. Again, any states that lie outside these ranges don't get counted. And because of the sign of y, states lying above the lower bound, counted by the left-hand term, are subtracted from the count, while states lying above the upper bound are added to it. Those that cross over the energy range of interest end up canceling each other out, and we're left with a positive count for those states which have entered the energy range and a negative count for those which have left. Having shown that this expression properly accounts for the number of states entering and leaving the energy range of omega of E upon a differential change in x, we can find the partial derivative of omega with respect to x by summing the expression over every possible value of y. Rewriting small omega sub y as large omega sub y divided by delta E, then multiplying and dividing both terms by the total multiplicity at their respective energy values, we find the sum gives us an expression for the average value of y. That is, y times the proportion of microstates with that value of y, summed over all values of y, is y bar. Having simplified the expression in this way, we find that it is in fact the difference between the product omega y bar evaluated at E and omega y bar evaluated at E plus delta E, all divided by delta E. This is the definition of the partial derivative of omega times y bar with respect to E, when you factor out the negative sign. What's more, negative y bar, being the average change in energy of the system as a function of x, is precisely what we defined back in Chapter 2 as the generalized force conjugate to x. So we've come up with a compact answer to our original question: how does the multiplicity change as a function of x? But we're 2 steps away from answering the question, how does the entropy change during a purely mechanical interaction? To get that answer, we need to turn this into an expression about the natural log of the multiplicity, and we need to use it to find the complete differential change, not just a partial one. The first step is straightforward. The derivative of the log of a function is just the derivative of the function divided by the function. So all we need to do is divide both sides of this equation by the multiplicity itself. Then the left-hand side becomes the derivative of the natural log of omega, and the right-hand side can be simplified using the chain rule. The first term we get is the partial derivative of the natural log of omega with respect to energy, and the second term ends up with a factor of omega in both the numerator and the denominator, which cancel out. Now, this first term depends on omega, while the second term doesn't. So you might guess that because omega is a really large number, this term is much, much larger than the second term. And that's right. One way to see this more explicitly is to consider that omega is usually proportional to the energy raised to the number of degrees of freedom, because the number of degrees of freedom is the number of different ways that energy can be arranged within the system. Each way of arranging the energy is a different microstate. So, the natural log of omega is proportional to the number of degrees of freedom, and its derivative with respect to the energy goes as the number of degrees of freedom divided by the energy. Thus we see that the first term on the right-hand side of this equation is greater than the second term by a factor of the number of degrees of freedom, which is so large we can ignore the second term without losing measurable accuracy. And if we again recognize the partial derivative of the natural log of omega with respect to energy as the definition of beta, our final result is the partial derivative of the natural log of the multiplicity with respect to an external parameter is proportional to beta times the generalized force that's conjugate to that parameter. Before we take the final step and use this partial derivative to find an expression for the exact differential of the entropy, let me just remind you that this result, which we got when varying a single external parameter, applies to any external parameter. Now, for our final step, we consider that the complete differential of the natural log of the multiplicity is the sum of its partial derivatives. Partial with respect to energy times a differential change in energy, plus partial with respect to external parameters times a differential change in the external parameter, summed over all the different external parameters. Since the partial derivative of the log of the multiplicity with respect to energy is our definition of beta, and our derivation just gave us that the partial derivative of the log of multiplicity with respect to an external parameter is beta times the average force conjugate to that parameter, we can factor out beta and recognize the term in parentheses as being the differential change in energy of the system plus the work done by the system. By the first law of thermodynamics, this is our very definition of the differential amount of heat absorbed by the system. Rewriting beta as 1 over kT, we come to our crowning result. Differential change in the entropy is the differential amount of heat absorbed divided by the absolute temperature at which that process took place. Mind you that all this derivation was assuming that the energy exchanges proceeded quasi-statically. For a purely mechanical interaction, there is no heat exchanged, and the entropy change is 0. But for any quasi-static interaction, we've now shown that the differential change in entropy is equal to the differential amount of heat exchanged divided by the temperature at which it was exchanged. This is our answer of how entropy changes when systems exchange energy. And it's also known as the second law of thermodynamics.